Hello, everybody. So this is like the last thing of Earth Science pretty much, except for the test tomorrow. So crazy. Congratulations, you've made it. This is a video that is going to go over the climate review packet. It's posted on Classroom. It was your assignment to do on Friday. I just want to go over it so that you know that you got the right answers and you're not leading yourself off in the wrong direction. So watch the video after you've done the review sheet. You'll get a lot more out of it if you are comparing my answers and your answers rather than just copying down my answers. The test will be tomorrow. If you have any questions about the test, please let me know. We're going to do it on a Google form, and you will do it during class time. So I will assign it, and it will be due as class is finishing up, just like everybody else in the room. So you'll be doing it at the same time as everybody else. I think that's it for now. I'm going to get to the review sheet. I have to stop this and move my camera a little bit. All right, so I'm going to try it like this. So your test will be on Tuesday, tomorrow. While the questions below should get you thinking, it's also a good idea to review the different notes and activities posted in bold to make sure that you fully understand the material. You may bring one piece of paper, 8 by 11, with handwritten notes to help you on the test if you would like. All the work for the rest of class will be due this Wednesday, January 27th. No late work will be accepted after that. If you are missing work and still need to turn it in, I would suggest doing these activities and these notes before the test as a way to help you study. And then I go over some of the topics that we will be covering in the test. So the following are some questions to help get those juices flowing, like I said before. So let's get started. So the first section is from Edpuzzle Atmosphere Lesson and Atmosphere Notes. So you can go reference those if you're not sure. List 3 reasons why the atmosphere is so important. Well, first, it gives us air to breathe. It keeps us warm. And we know that that's from the greenhouse gases. And air to breathe, keeps us warm, and wow, I'm having a little brain malfunction. I just thought of it a second ago. Air to breathe, keeps us warm. What's the third one? Oh, protects us. Sorry for that. Protects us from the sun's harmful rays. And we learned about that with the ozone layer. Remember that ozone is kind of like acting like a shield to protect us from the sun. So these are reasons that the atmosphere is so important, even though sometimes we don't even realize it's really around us. How does the Earth hold on to its atmosphere? Gravity. Basically just being pulled down by gravity, and Earth's gravity is directly related to how much atmosphere there is. If it was a bigger gravity, there'd be more atmosphere, and if it was a smaller gravity, we'd have a smaller atmosphere. Okay, then we have a pie chart, and which gas has the highest concentration? So that would be this big chunk right here. It's 78%, and that is nitrogen. Most people think that the atmosphere is mostly made of oxygen, but now you know that's not true. Which gases have the smallest concentration in their atmosphere? Less than 1%. So this is the 78. The 21% here is oxygen. This is nitrogen, oxygen. This 1% is argon. And then less than 1%, it's not even on this graph. It would just be like maybe one little line. That's greenhouse gases. So greenhouse gases aren't very common in our atmosphere, but they are very, very important. So which gases have the smallest concentration? Less than 1%? Greenhouse gases. Okay. The next note section comes from air pressure notes. And I'm just asking you to label where the high and low pressure would be in this diagram. On the notes, you actually drag these, but you can just write it on your paper. So low air pressure is where air is going to be lifting because it's not pushing down on your head. It's lifting off. So that means it's a low air pressure. So the lowest air pressure is going to be right here where this air is lifting off of the stove where it's really hot. Okay. And then where's high pressure? Well, there's actually two high pressures in this. High pressure is where the air is falling and pushing down, like it would be pushing down on your head. That'd be high pressure. So you could either label it here or here as high pressure. So two choices for high pressure. Okay. And we know that this happens not just in a room. We learned that this can happen on a global scale where it's rising low pressure air, where it's really hot at the equator. Then it moves across the planet in the upper atmosphere. And then eventually it falls down and creates high pressure systems. And those are right on the deserts. Okay, page 2, or paper 2. Okay, air always wants to be in homeostasis. This means that if there is high air pressure and low pressure area, they will try to equal out. Which way does the air move? High pressure to low pressure or low pressure to, or low pressure to high pressure? Think of a waterfall. Air will, sorry, I'm having some issues. Air will always move from high pressure to low pressure. Just like a waterfall, if this is like a side view of a waterfall, right? The water is going to move from up here where it's high, and then it's going to fall down here to the low area. It's the same thing with air, and I tried to get you to think of that when we were talking about air being like an ocean. When air is moving from high pressure to low pressure along the ground, we call that, and P.S., this is my least favorite type of weather, wind. So when you feel blowing on your face, basically what's happening is there's high pressure in one area, low pressure in another area, and that wind is moving, trying to get to that low pressure area. So that's why, and we know that low pressure is rainy and high pressure is sunny. So if we have a big change in weather from like a really rainy day to a really sunny day, there's usually a lot of winds in between those 2 days because there's big pressure changes. Okay, from the Hadley cell mapping activity. Where do most of the world's rainforests occur? Along the equator. Why? Because it's very warm there. So air is rising. Because we know that when warm air is less dense, so it's going to rise. And when it rises and it's warm, it brings up lots of moisture. Lots of evaporation. And when all that rain gets up into the air and it starts to cool off, it makes lots and lots of clouds and it rains a lot. So I'm going to say water vapor cools, turns into clouds, and that means it's going to rain a lot. So it's raining a lot along the equator because it's very warm, air is rising, and as it rises, it brings up all that moisture. And as it gets higher in the air, it starts to cool off, makes clouds, and rains a ton. Where do most of the world's deserts occur? You don't have to, sorry, that's not really a great question. You don't have to say exactly where they occur, but you can say along similar latitudes. right? Like they're all occurring on those same lines. And in this Hadley cell mapping activity, it was along those purple lines. So they're all occurring on the same latitudes. And why are they doing that? Well, the air rises at the equator, rains out all the water, and then, so air is rising. It makes lots of clouds here along the equator, and it rains all the water out. But then there's more coming up behind it. So in a convection current, this air has to move to the left and the right. And as it does that, it starts to cool off, and eventually it's going to fall. Remember, this is the same air that was here. Then it moved over here, kept moving, and then that same package of air fell down. Does it have any water in it anymore? No, because all the water got rained out over here. So this is just really, really dry air that's falling, and this is right where the deserts are. So what I would say for why, if I was like writing out an answer, they occur there because it's high pressure and the air is very dry. It all got rained out at the equator. All right, number 10. Does high pressure mean a sunny, clear, dry day or a wet, stormy day? One of my students says high and dry. So this would be a dry, sunny day. So those beautiful July days that we have, those are high pressure days. Days that we have in the winter that are bluebird days, when if you like skiing or spending time outside, those are high pressure days. When the sun is out, it's high, it's dry and it's sunny. A low pressure day, low pressure is when we have storms, when we have rain, snowstorms. So that storm that we got that this past weekend where we got or 2 weekends ago, I guess, where we got like a foot of snow, that was a big low pressure system. So low, the same student that says high and dry, he says low and flow. So the water is flowing. So low pressure is a stormy day. Like hurricanes, super low pressure storms. So that means that air is rising and it's going to be raining a lot. In Vermont last weekend, there was a rainy, snowy storm. Do you think this was a low or high air pressure system? Well, I just told you what it was. It's a low pressure system. Okay, from the Greenhouse Gas Lab. Why are greenhouse gases important for the planet? They keep us warm. Otherwise, at nighttime, we would be like negative in like 400 degrees Fahrenheit. So it would get so incredibly cold here that we would freeze. We'd probably die. So probs die. So greenhouse gases are super important. They are in our atmosphere and they keep us warm. But how are they dangerous for the planet? If we have too many of them and we keep adding more and more, and their job is to keep the planet warm, they're going to start warming up the planet. So greenhouse gases can be dangerous because if there are too many, the planet heats up too much. Like they do their job too well. Okay. All right. Okay, number 15. Draw a picture that shows how greenhouse gases are able to warm up the planet. So I have my ground. We have a nice, beautiful tree. Sun. All right. So it all starts with the sunlight coming in during the day and heating up the planet. So I'm going to label this sunlight. So the sunlight is coming in. But if the sun just gave us heat and heat and heat and heat, and we didn't give any heat away, the planet would get really, really hot during the day. So to equal it out, we have this stuff called infrared, which hopefully sounds familiar from the light unit. Infrared, or sometimes people call it earth light instead of sunlight. And that is going to be giving that heat back into space. So the sunlight comes in and the same amount of energy goes back into space. And that way, it doesn't get too hot here during the day. But if we gave back all the sunlight energy, that would mean that at night when we didn't have any sun, we also wouldn't have any heat from anywhere, and it would be really cold on this planet. That's what happens to Mercury during the day and night because it doesn't have a planet. It doesn't have an atmosphere. It can get up to or down to like negative 400 degrees at night and up to 800 degrees during the day. We're really lucky that we don't have that because we have these greenhouse gases. So we have the sunlight coming in, we have the infrared going out, and then in our atmosphere, we have all the greenhouse gases. So maybe some CO2s, maybe some H2O water vapors, and maybe some methane, CH4. Okay. Now what happens is as the sunlight comes in and then bounces away as infrared or earth light or heat is another thing that we could call this, right? Like you are giving off heat. Everything else was giving off heat as well. So what happens is the sunlight comes in and this infrared tries to escape. But what happens is sometimes it might escape, but sometimes it might hit a greenhouse gas. And when it does that, it warms up this water vapor. So this heat that was going out hit this water vapor, warmed it up, and then what happens is at nighttime, this water vapor can actually send the heat back to Earth. It's called it re-radiates. Okay, so some is coming in, some might try to escape, hit another greenhouse gas, warm it up, and then at nighttime, this carbon dioxide will send its heat back to Earth. Some might come in, and some might escape right out. And that's fine. We want some of it to escape because we don't want to hold all of the sun's heat. Then it would get really hot here. But some of it is going to hit these greenhouse gases, warm them up, and re-radiate them back. When it becomes a problem is when we start adding more and more greenhouse gases and we start blocking these exit strategies for all this heat. So maybe we, drive our cars and we add more CO2 and it kind of blocks this exit. So next time when this tries to exit, it's actually going to warm it up and send the heat back to the planet. So when we start plugging up these holes from more greenhouse gases, that's how we can kind of make this planet warmer. Okay, this next graph is from the Specific Heat of Water Lab and Graphing Climates. And it says, use the graph to answer the following questions. So the first thing I like to do is I just look at the graph to see what I'm looking at. So it has average temperature over here, and it has month on the X. So I'm looking at average temperatures in different months for two different places. And it doesn't necessarily tell me where they are. So Y and Z. Which city is more likely to be near a large body of water, Y or Z? And without me telling you, you should actually know that the answer is Y. And that's because of the high specific heat of water. So 17, use word specific heat of water to describe why city Y is warmer in the winter but cooler in the summer. And that explains what's going on here. It's warmer in the winter, so Y is warmer in February, March, and April, but it's actually colder in June and July. It's also a much straighter line than this one that is topsy-turvy. So the water has a high specific heat, which means it takes a long time to cool down in the winter. So all summer, it's like a big bathtub, and it's heating up and heating up and heating up from the summer heat. And then as soon as like it stops being warm and it becomes like September, October, that thing starts to cool down, just like the air, but it takes a really long time. So you can see, like in September, it's still pretty warm, and in October, it's still pretty warm because that water is still warm, and it's basically acting like this big bathtub that's just giving off heat to the city. So it takes a long time for heat to cool down, or for the water to cool down in the winter. Okay, so then it's cooling down, it's cooling down, it's cooling down, it's cooling down. Okay, now it's April, so it's starting to get warm again. But we can see that city Z is getting warm much faster than city Y. And city Z actually overpasses it. And the reason for that is because water has a really high specific heat. So not only does it take a long time to cool down, water also takes a long time to heat up. So kind of through the spring months, instead of acting like a big hot bathtub, it's acting like a big cold ice bathtub that's kind of giving off colder air to the city around it. So it keeps it much cooler. So if you live near a city, let's see, I'm going to write it over here. Near a body of water. Near a body, I'm writing and speaking is not working so well. Near a body of water, your temperature is going to be a lot more stable because that high specific heat is going to keep it at like a much more stable level. Whereas if you live not near a big body of water, you don't have the water to keep you stable. So in the winter, you get really cold, just like that sand lab. But then when the sun comes out and it gets hot, it heats up really quickly, just like sand. And then the sun goes away and it cools back down really quickly. It doesn't have this nice water to keep it stable. So when you're looking at graphs like this, you know the one that's more stable is the one that's going to be near a big body of water. All right, last piece of paper. So from the weather and climate notes, number 18, what is the difference between weather and climate? Basically, the short answer is time. Weather happens every day. It's what's happening on your head right now. I'm looking out the window. It is snowing. That's the weather. It's what you should wear for the day. Climate is what you expect to happen. It's what's usually going to happen. So climate describes what to expect, right? Like if you go to the Bahamas, you're going to be warm. If you stay in Vermont in January, you might be cold. So weather happens every day. Climate describes what to expect. It's an average of 30 years of weather data. So you take the weather for 30 years, add it all up, figure out what the average is, and then you have climate. So are the following sentences talking about weather or climate? It's only 40 degrees in July. This must be global warming. That's weather. Even though it says global warming over here, it's talking about 40 degrees in July. That's a specific day. It's not usually 40 degrees in July. So that's the weather. I can't wait to ski in Alaska. That would be climate because it's usually cold in Alaska. I love the sun shining on my face. That one's a little tricky, but remember that weather is what's happening on your head. So this would be weather because the sun is shining on the face, theoretically right now. Maybe if they said, I love the sun shining on my face and therefore I want to move to Florida, then it might be climate. But the sun shining on my face would be weather. What a beautiful March day. Weather. March isn't usually beautiful in Vermont. Climate. My least favorite month. I'd love to live in the Bahamas where it's warm. Climate. Okay. From climate change notes, what are the 4 things that determine the climate of an area? So climate, whether humans are here or not, climate would happen, right? Like the North Pole and the equator are still going to be the North Pole and the equator temperature-wise, even if humans aren't here. So the 4 things that determine it naturally, what climate should be, is latitude. That's how far from the equator you are. So the North Pole has a different climate than Brazil because they're on different latitudes. Elevation is another one. So that would be how high up on a mountain you are, right? Like the top of Mount Mansfield has a different climate than in Essex. Because at the top of Mount Mansfield, it's much windier, it's much colder, there's different types of trees. So elevation. Another one is how close you are to water or proximity to a body of water. Right? We talked about how the climate of one area, like Burlington, is going to be a little bit warmer and a little bit more stable than a place like Essex, which doesn't have the water to stabilize it. So if you're close to a body of water, your climate's going to be more stable. And then the last one is like air pressure and convection currents and where you are in that. Because if you're somewhere where the air is always rising, you're going to have a very rainy climate. And if you live at a high pressure area where the air is falling and dry, you're going to live in a desert. So are there natural climate zones? Yes. Even without humans, there would still be deserts. There would still be the North Pole. There would still be rainforests. What evidence do scientists use to prove that climate is changing? Ice cores. People were not alive 800,000 years ago, so the only way that they can compare today's climate to past climates is through ice cores. How are humans changing with climate? We are adding greenhouse gases. Greenhouse gases to atmosphere. We are doing deforestation, so we're cutting down trees, and those trees would normally be sucking the greenhouse gases out of the atmosphere, but we're cutting them down. So now not only are they not sucking anything in, but they're also being burned or whatever they're being used for and releasing that carbon. All right, last page. How are fossil fuels made? They're made from dead plants from before the dinosaurs that got buried, and then millions and millions of years passed, and all the pressure changed it into fossil fuels. Changed to fossil fuels like oil and natural gas and coal. How are humans disrupting the carbon cycle? So we are taking out, the fossil fuels are made with tons and tons of carbon because they're just plants that got buried. So they've got tons of carbon stored in them. And the fossil fuels are basically in timeout. Fossil fuels are in timeout. They have not really been a part of the carbon cycle for millions of years. They've been stuck underground. They haven't been able to be participating in the carbon cycle. But what humans are doing is we are drilling down and we're pulling all those fossil fuels out of the ground. And we are taking out those fossil fuels, taking out all that carbon that's been in timeout, and we're releasing it into the air. So humans are getting the carbon out of timeout and letting it go play with the rest of the carbon. And that means that there's extra carbon. There's more carbon in the atmosphere than there really should be. So I'm going to say too much carbon in atmosphere. Are humans a part of the carbon cycle? Yes. We can't survive without carbon. Our bodies are made of carbon. We eat with carbon. We release carbon when we breathe. So yes, we are a part. And yes, plants are also a very important part of the carbon cycle. What are some common items that you use that are made out of oil? Oh, the list goes on and on here. Let's see. Glasses, like the ones you put on your face. Athletic clothing. Athletic clothes. Leggings. Tires. Toothbrushes. Gum. I don't know. All plastic. That covers a lot. I'm just looking around my room right now, like a remote, my pen, my dog's collar. So the list goes on and on and on and on here. Gas. Got to include that one. Okay. What does this graph show? So if I look at it, I'm seeing that there's the year and there's CO2 parts per million. So it's showing carbon dioxide increasing over time. And why did it happen? It happened because of humans. Because humans burn fossil fuels that release carbon dioxide into the air. If we continue adding more carbon to the atmosphere and burning fossil fuels, what will happen to global temperatures because of the greenhouse effect? Well, we know that CO2 is a greenhouse gas. So if we keep burning CO2, if we look back at our picture here, we're going to start closing up these holes. We're going to start re-radiating this heat back to the planet. And what's going to happen? Global temperatures will rise. CO2 will be blocking the exit for the infrared. And so it will warm us up. All right, that's it. Let me know if any of those didn't make sense to you or if you have any questions. The test is tomorrow during class time, 1:25.